Hello everyone, I'm Romina Santi, a PhD student of Design Department of Politecnico di Milano. In this video presentation, I will show you the major project of my research group, the development of sustainable materials and processes, the case study of polypaper. The research team includes me, Professor Silvia Farè, Barbara del Curto and Alberto Cigada. The project was born from the findings and intuition based on the market, on today's realities, and the problems related to the disposal of packaging waste. The classes of packaging materials are numerous since there are many functions that packaging materials must fulfill. In many industrial cases, different classes of materials are usually combined in a single package. For example, corrugated cardboard, printed paper, polyester foam, and low-density polyethylene, and various other plastic components. Each of those materials follow a different path for collection, disposal, and recycling. If used jointly in a single package, it can happen that they are not distinguished from the consumer and disposed jointly in the same waste stream. In a sustainable design process, different packaging materials must be separable, separated by the consumer, and collected in a specific recycling channel. Nowadays, designers are asked to select, but also to combine and develop responsible packaging materials. As you know, the circular plastic market is a growing trend that will keep this for the future years, and the main area of development consists in packaging sector, and there are environmental, technical, and legislative reasons. In the same way, is increasing the ability to recycle, and the largest recycling channel is the paper industry, both for its virtuosity and the percentage of recycling rate. Our solution is polypaper. The name polypaper was born from the idea of combining the process of thermoplastic polymers and the virtuous end of life of paper-based materials. The basic idea is designing a material suitable for carrying out all the functions of packaging: contain, protect from the mechanical shocks, transport, and recycle. The polymer selected as matrix of the composite is a formulation based on water-soluble polyvinyl alcohol, PVA. This thanks to its biodegradability, biological and ecological compatibility, excellent adhesive properties, chemical resistance, and gas barrier properties. The selected reinforcement is microcrystalline cellulose (MCC), environmental friendly product gained from replenishable raw materials able to improve the mechanical properties of the matrix. So, starting from a dry blend of the two materials, we use extrusion to get a first response and result of polypaper. Polypaper by extrusion can be produced in pellets, filaments, and sheets. In this video, you can see the extrusion process. Thanks to its composition, polypaper is also water-soluble. In the following video, a vase made of polypaper is immersed in water, and after 2 hours the vase will collapse and then dissolve. The water solubility of polypaper allows to recycle it with paper and cardboard. Polypaper sheets can also be thermoformed or injection molded. Or polypaper filaments can also be 3D printed with conventional fused deposition modeling, as the video shows. Polypaper can be 3D printed with low temperatures, high speed, cold dish, without lacquers and fan-off. An innovative feature figured out by 3D printing is that printed flat objects can be formed by heat treatment in different shapes. The touch is not like plastics, it's paper-like. 3D printed objects can be smoothed by wiping with a wet cloth. Polypaper can be strongly welded with water in few seconds to itself, cardboard and wood. In addition to traditional processes, we develop an innovative process exploiting the property of the selected materials, water solubility. This new technology, called water shaping, allows in particular to improve the resistance to shocks and the capability to absorb energy. This is a very important property for packaging. In the first step of the process, a certain amount of polypaper pellets is manually added with a third weight of water. Then, in step 2, the blend pellets water is mixed for 15 minutes. In step 3, before 1 hour at room temperature, the blend have to be put into the desired mold. In step 4, after closure, the mold is heated at 60 degrees for 3 hours in order to obtain evaporation of the excess of water. The objects are then extracted from the mold. The granules are now firmly bonded, and the material acquires high impact resistance. It's also possible to expand the pellets of polypaper, adding the 2% weight by weight of expanding agent into the starting dry blend of polypaper before extrusion. The porous structure of the expanded foam is able to absorb a high amount of energy during the compression deformation due to a peak load effect connected to the expanded structure and to the granular shape. The macrostructure of the compacted granules after wetting and compaction appears similar to that of the expanded polystyrene, a material notoriously capable of absorbing shocks. So, compression tests have been carried out on these samples. It is possible to observe that increasing the percentage of cellulose increases the mechanical properties. The addition of an expanding agent while decreasing the apparent density of the material causes an increase in the mechanical properties too. The stress-strain curves can be integrated to calculate the absorbed energy as a function of the applied stress. Simplifying, this video shows the ability of polypaper disc to absorb shocks. As conclusion, polypaper is produced using recycled cellulose fibers and can be recycled with paper and cardboard in a circular economy model. Polypaper permits the realization of monomaterial packaging thanks to its versatility of production and properties. Water shaping permits to realize complex shapes without molds or complex machining operations. If dispersed in the sea, polypaper does not contribute to the accumulation of litter because of water-soluble. Here you can find our contacts. Don't hesitate to contact us. Thank you.